Hello, my name is Benjamin Martin, Secretary General of the Ocean Thermal Energy Association, or OTEA. OTEA is a volunteer organization providing a means for collection, coordination, and dissemination of information for ocean thermal technology stakeholders, with over 400 members from 46 countries and regions. Ocean thermal refers to technologies utilizing the naturally occurring temperature gradient in the ocean to achieve effects useful to society. The three major technologies are seawater air conditioning, (CWAC), ocean thermal energy conversion, (OTEC), and low temperature thermal desalination, (LTTD). More broadly, these can all also fall into deep ocean water, (DOW) use. OTEC is a method of power generation using the temperature difference between surface and deep ocean water. There are various cycles and configurations. CWAC uses the cold aspect of deep water for cooling more efficiently than standard cooling devices. LTTD uses a system similar to open OTEC, where a vacuum chamber lowers the boiling point of surface ocean water to create steam that is distilled in a heat exchanger with deep ocean water. For this presentation, we will focus on the previous three technologies, though the largest number of DAO intakes worldwide are used for productive uses such as water bottling, cosmetics, and fishery. Currently, there are at least 38 sites around the world, with 45 intake pipes to at least 200-meter depth around the world. Japan has 18 pipes, South Korea and India both have 8, Taiwan has 5, and French Polynesia and Hawaii have 3 each as well. This does not include surface intakes.
To our knowledge, this is the first time the worldwide deep water intake pipes have been listed together. We appreciate the cooperation of stakeholders in each country for sharing the status of DAO use, which shows great promise for island communities to meet energy, food, and water needs.
In terms of direct energy production, OTEC is a group of technologies that have been under development around the world for years, but is still at a pre-commercial stage. The technology can be used where there is an annual average 20°C temperature difference, so many developed countries cannot utilize it. Still, as the ocean is vast and it stores solar energy, the resource potential is sufficient for island and coastal communities in the tropics and subtropics to achieve energy independence. Closed OTEC, as seen on the left, uses a low boiling point working fluid in a closed loop. The breaking fluid is warmed by surface ocean water, which in turn is renewably heated by solar radiation. The facility's working fluid evaporates to vapor, which expands in a turbine to create electricity. Next, the vapor is condensed back into a liquid in a second heat exchanger, with the cold provided by deep ocean water. As a liquid, the working fluid can be reused in a continuous cycle. Alternatively, the open cycle uses a vacuum pump to lower the system pressure, lowering the boiling point of surface ocean water. When exposed to vacuum, the surface water flashes to steam, which expands a low-pressure turbine to create power. The deep ocean water condenses the steam back into a liquid, producing desalinated water. The International Energy Agency's Ocean Energy Systems Program released a white paper on OTEC this past year that highlights the technological readiness of OTEC to meet island energy needs and outlines recommendations for further development. Next, I will briefly share the status of the known OTEC facilities around the world. The Okinawa OTEC demonstration facility was established in 2013 and is still operational. It is a 100 kilowatt class demonstration with double ranking configuration. The Makai Ocean Energy Research Center, located at Nelha in Hawaii, has a 105 kilowatt rated capacity and is the largest OTEC facility to be connected to a US grid. In September 2019, the Korean Research Institute of Ships and Ocean Engineering, (KRISO), tested OTEC equipment offshore prior to establishing an onshore facility in Kiribati. The test holds the world's largest OTEC output so far recorded. In terms of research, the equipment at the Institute of Ocean Energy, Saga University, is the world's longest-running equipment. Established in 2003, it is used for technology development that has supported many follow-on projects. In 2017, the India National Institute of Ocean Technology, (NIOT), established an LTTD and OTEC test facility in Chennai, following on from years of research in ocean thermal technologies. In Mexico, Simi Oceano established a lab-scale facility for education and research as the first prototype in Latin America. Japan and Malaysia, under a SATREP's joint research project, have developed a hybrid OTIC lab that is awaiting installation in University Putra, Malaysia. At the end of 2021, NIOT announced a contract signing for procurement of a 60 kilowatt gross open cycle OTIC equipment. These 8 facilities and labs are not inclusive, as there are other private labs and ongoing projects. CWAC is a system that can drastically reduce electricity used for cooling through the use of existing cold, deep water resources. Fresh water is cooled in a heat exchanger, which then travels to buildings with cooling demands, such as hotels. So far, this technology has mostly been used in French Polynesia, though similar installations can use alternative cold sources, such as lakes as well. In 2006, the Intercontinental Bora Bora Resort established a CWAC system for the resort, resulting in a 90% reduction in electricity use when in operation. Similarly, the Brando Hotel on Teteroya was completed in 2012. The intakes for this facility go to a depth of 960 meters. Also in French Polynesia, a CWAC system with a 3.8 kilometer intake dubbed the world's longest CWAC was completed at the end of 2021 to cool the Taon Hospital on Tahiti. A CWAC system has been reported to be contracted for the La Reunion University Hospital, located in the Indian Ocean as well. LTTD is a method of desalination that avoids many of the challenges of reverse osmosis systems in terms of operation and maintenance. The system removes only about 1% of ocean water as freshwater, leaving the output easier to manage as well. As with open cycle OTIC, surface ocean water flashes to steam in a vacuum. The resulting steam is condensed back into a liquid in a heat exchanger, deep ocean water creating distilled water. In Japan, LTTD has been researched at IOES with a small-scale lab installed next to the Okinawa OTIC demonstration facility. The major pioneer of LTTD has been NIOT, leading with an initial plant on Kawarati to provide fresh water for the remote island. After successful operation, 2 more plants were commissioned with a 100 kiloliter per day facility installed at Minikoi in 2011. And also at Agati, these facilities take a unique approach to providing fresh water in remote locations, with the nearshore environment managed with raised bridges rather than tunnels or trenches. From 2020, Pelteni Island's LTTD came online, producing 150 kiloliters per day, part of a second phase of installations that are currently underway. Amini Island's 150 kiloliter facility is also currently under construction and nearing completion. Jetlat Island is also in development. Katabat Island will also have a similar facility. Androth Island will complete this second phase, bringing the operational LTT facilities to 8 in India, a huge accomplishment towards water security. Although each location and technology was only briefly introduced, I hope my presentation today has provided a glimpse of the potential and wide applicability of ocean thermal technologies to meet our current and future energy and resource needs sustainably and cleanly. Thank you for participating in this 12th Hawaii Okinawa Clean Energy Workshop. To find out more about ocean thermal technologies or to join the OTA, visit us at oceanthermal.org.